later. Okay, so today we're going to be looking at seismic tomography, but more focused on ambient noise tomography because of the advantages it has, and it's a bit more involved. So I'm just going to take you through the processing and everything, like mostly just explaining because it's difficult to do the practicals online. So, but then if you want to work on this, then it's a good at least first tutorial to encounter, so you have an understanding about what's going on. So I mean, we already talked about the representation theory, and the goal of seismic tomography is mainly to reconstruct, to retrieve the, oops, wait, where did this go? Just a moment. Okay. Is to reconstruct the Green's function. Oops, no. Sorry, just a minute. Okay. So we want to, oh, wait, just, I'm just having problems here. Why is not? Okay, I need to do this now. This is always, okay. Sorry, just a moment. Oh, I got disconnected.
Why?
I'm still connected?
Yes, you are connected.
Yeah, I can hear you. But I
but
cannot see anything, like the Zoom thing is gone from my, probably.
Professor, hello. This is Marco from the video team.
Yeah.
Is there anything I can help you with?
Not quite. It's just my Zoom. I cannot find my Zoom box, but okay, I'll try to just go ahead without it, because I cannot find where I need to annotate and change the colors and everything. So.
Oh, okay. Okay. So it's on your side.
Yeah. So probably let me just disconnect and connect again.
Okay.
But even the disconnect button is gone. Can you disconnect me? Hello?
Yeah, I'm here.
Yeah, because I cannot see anything. I cannot even leave the meeting or anything. So
that is strange. Let me see what I can do. Well, you are co-host.
Yeah. Oh, okay. Right.
So you have access to everything. Right now you are sharing the screen.
Okay. Yeah.
But all we're seeing is gray lines.
Yeah. Okay. I think I'm back in.
So you may want to stop sharing the screen.
Yeah. Okay.
How many monitors are you using?
2. That's what it's causing the problem. So now I just disconnect one and only, yeah. Okay. Now it's only one now. Okay.
No, and the connection is also pretty unstable today.
Oh, okay. Yeah, I got the email about the.
Yeah, they're working on firewalls and updates.
Okay, let me check. Okay, I think this should be fine. Okay, so. Okay, good. So yeah, so then the goal of seismic tomography is to reconstruct or estimate the Green's function, given a seismogram, from the Green's function. And there are different types of tomography. We can look at the body wave tomography, which is mainly P wave tomography and S wave tomography, where in this case we retrieve the P wave velocity, and in this case the S wave velocity. Okay, and then we can also get some information about the Green's function using the surface wave, which is a surface wave tomography. So yesterday we looked into the dispersion curve estimation, And 1D, what we call that one is a 1D velocity models, you know. But when we talk about tomography, mainly we have, say, an area, and we have some stations within this area, okay? And then we have some sources. Let's say we have one source here. So let's say if there is an earthquake, then the wave travels from the source to these stations, okay? And we have another, if we get another earthquake here, this one will also, let me change the color, will travel from this source to this station, okay? So then the goal of tomography is just to constrain the velocity of area of interest, our region of interest. So if we're interested in getting the 2D or 3D velocity structure of this, then in this case, we're going to combine the waves coming from this earthquake and this earthquake, okay? And then the P wave tomography is just using the P wave part of the waveform, or the S wave tomography using the S part of the waveform. And then surface wave, we use the surface wave part. And what we go, you remember, I think in the Monday lecture when we're talking about the acoustic tomography, where then we have to divide our rectangular box into some small, I don't know if this is making any, some small boxes, okay? So then, sorry for the mess. Then the goal is to use this rays and these station locations to constrain the velocity of each of these small boxes, okay? So then our model parameters will be to constrain the velocity of this box. So in this case, 1, 2, 3, 4, 12 boxes, okay? And then the data is it's coming from the rays. And you can see that if we, let's say in this case, in this simple case of 3 stations and 2 events, then let's say if we want to constrain the velocity of this box, okay, of this fourth box, there is no wave passing through this fourth box, and there is no station here. So we definitely have no information about this. We cannot really constrain this model parameter because there is no data in there. And this is the issue with tomography. So when you're making a seismic tomography, you need as many sources as possible, okay, so that it provides some information and some constraint on the model parameters in each of these boxes, okay? And this information is coming from, say, P waves, S waves, or the surface waves. And you need also more stations so that you can really constrain each of these model parameters, okay? So tomography is just the 2D or 3D version of these 1D velocity structures that we looked at. We'll see some examples, so you can then color scheme each velocity value, and then you can just interpret your results in terms of using some nice graphs, okay? So traditionally, you require an earthquake, as we saw in these cartoon diagrams. You require an earthquake, but it's sometimes in some areas you don't have any earthquake happening. So then, how do you retrieve a velocity model if that's what you're interested in? So the ambient noise method is just a way of retrieving this green function without a need for an earthquake source. So in this kind of tomography, we take away the source, which is the earthquake, and just try to use some processing technique to retrieve the Green's function, okay? That's what we're going to look at. So now we're just dealing with a wave. We're not dealing with the source. So we look at some natural sources of seismic signal. So what forms this seismogram, this displacement? Yes, there is an earthquake. Of course, when the earthquake happens, the seismic waves generate some displacements. And then you have some noises due to atmospheric disturbance, some solar disturbances. and so forth and so on. So all these all these noises or these sources are recorded on a seismogram. If we look at say a 1-day record of a seismic section, you see that majority of the record is made up of noise, and then just a small part of the data is just an earthquake, because the earthquakes are infrequent. So, you know, it's just a small part. So most of the time, we're just interested in this part of the seismic record, which we call data. And then there is a huge amount of the data that is noise that usually we throw away. Okay. And you can imagine this is just 1-day record that we have an earthquake. Most of the time there is no earthquake at all. So you can go months without, let's say, without any a major earthquake, strong earthquake happening. So then all your data seems like noise. And if we could find a way to make use of this noise, that would be great, because we're recording them, we're saving them. And that's where ambient noise tomography comes in, because this data is already available, okay? So then we have to find some uses for the noise. And yeah, so how do we go about making use of this noise? Is what we use a processing method, that's a seismic interferometric method. So what is it about? This is just a cross correlation, okay? Between two, so we just do a cross correlation between two records, that's data recorded at two seismic stations. And this cross correlation will help us to retrieve the Green's function that describes the direct wave propagation between the two receivers. So what it means is that, you know, you have your seismic stations here, and you record some noise every time, because there is these natural sources like the atmospheric disturbances and everything, and also anthropogenic sources like, I don't know, mining, you know, traffic and everything. So the noise source, the receivers are recording continuously. And then the seismic interferometric method is saying that if we take this source, this data, and this noisy data, and we do some processing, and we cross correlate this data with that data, then we can retrieve some resulting signal, okay? That is a signal that constrains the Green's function between these two stations. So we can retrieve the Green's functions is the elastic properties of the medium, okay? That's where the information is contained. So we can constrain how the elastic properties of this medium between the two stations. And this is technically what we get from an earthquake. So let's say in the case of an earthquake, we can imagine that this is the source that has some properties, and it's coming with its moment tensor, okay? And this is a station. So this wave propagation brings us information about the Green's function of this medium. And then in the case of the ambient noise, it's just saying, okay, if we cross correlate, if we do some pre-processing and cross correlate these noises, then we can take one of these stations as the source and this another station as the receiver, and the signal that we get gives us the Green's function between these of the medium between these two stations. Okay, so the retrieved Green's function contains information of the wave propagation, okay, between the two mediums. So this is it. So in the end, this is a way of not dealing with a seismic source, and then we can, without a seismic source, we can get some information about the medium. Okay, so just a bit more explanation. Say we have two stations, okay, at A and B, two seismic stations at A and B, and a noise source at X. Then at time 0, if we generate a wave, then the wave will be recorded at station A at TA, and then at a further time at station B, okay? And the point is, if we remove this source and we take the 0 time as coming from station A, then the time difference that this wave was, we can find the travel time between the two stations by just the difference between the time, the travel times recorded at these two stations. So in this case, we are just only interested in the time it took the wave to propagate from station A to station B, okay? And in the other case, in the reverse case, if the source is behind station B, then it will be recorded earlier in station B and a later time in station A. And again, if we can just find the travel time between station A, station B and station A. And if this medium is homogeneous, then by the reciprocity theorem, the travel time should be the same, okay? And if the two sources are present, then we can find the time difference between these two stations. So we can really constrain only the time difference between the two stations. And this is the information that we want. How it works. Okay, so turning noise into signal. So in the case I explained, the source is right in a horizontal line between, in relation with the two stations. But then what happens if the noise is offset? Okay, if there is a noise source here, then in this case, we will record at A and at B. But then there is no way of retrieving the travel time between these two stations, okay? But the good thing is the noise sources, it's all around. So if also another source is here, then at the same time, these sources don't provide any information between the two stations. We just record them. But if we do the cross correlation, so let's say we record all these source noises around these stations. Then if we do the cross correlation, these noise sources that are coming off, not like off some angle, coming from just a bit off, not in like a straight horizontal straight line or some area, it's in the next slide. These source of noise will cancel out each other. So there is a destructive interference between these sources, such that all the Green's function is just made up of noise sources that are just around these two stations. Okay, we'll see in the next slide. So then, sorry. Yeah. So then the most constructive interference from these sources is coming from just the sources that are in some area, in some region around the horizontal line connecting the two stations. And then the sources from the off that are way in at some angle will cause a destructive interference, and then they will cancel out. Okay, and then we'll find that in this case, so this is a good thing, a good image. So then all these noise sources will cancel out, and the signal will only come from the sources that are in this region behind the two stations. And then what we retrieve is a signal, that's the result of the cross correlation. It's a signal that appears as such that there is a source at A and waves generated that are propagating to B, okay, that are coming from these noise sources behind A, and another signal that behaves like a source at B and propagating to A. So this is the two parts of the cross-correlated signal, which is the positive time lag. So we have one signal in the positive time lag, and another signal in the negative time lag. Okay, that's just this. Let's say this positive one is just the signal that behaves as a source at point A and traveling to point B, and the negative one is the one that is a source at point B traveling to point A. Yeah. And so Usually in the analysis, we consider a homogeneous distribution of noise sources, such that the noise sources that are at some angle will cancel out, and then we just get the wave from here. And in this case, when the noise sources are distributed homogeneously around these two stations, then the results of the cross correlation, the waveform that we'll get, will have the same time. Okay, so the time difference that it requires for the waveform to travel from station 1 to station 2 will be the same as the time it requires the wave to travel from station 2 to station 1. And another thing we see is that the amplitudes of the signal will be the same. Okay, when the noise sources are homogeneous, the amplitudes are the same. So this is the result. In the case where you have the noise sources behind one station is more than the other, this is the inhomogeneous case. Let's say if this is the ocean, so you have all the ocean waves coming in this way, okay, then definitely the noise sources here are greater than the one behind station 2. So in this case, what happens is that the signal that you retrieve when you cross correlate the noise from station 2 and station 1 is such that the two signals will have the same travel time, okay, between the two stations, but then the amplitudes will be different. You see, because of the majority of the noise sources are occurring behind station 1, the amplitudes here recorded at station 2, it's bigger than in the case where the noise sources are less, and then the amplitudes are decreased. In the reverse case, where the similar thing happens in the reverse case, where also the noise sources appear are mostly concentrated behind station 2. In this case, then the one in the signal in the negative time lag will have a greater amplitude than the one in the positive time lag. But then the point is the travel times are still the same. Okay. So what's this correlation between? Yeah. So what's contained in this signal that we have retrieved? Okay. Research have shown that most of the time, this signal is made up of surface wave signals. Okay, we are retrieving the surface wave part of the Green's function. Yes, some work have shown that we can also get the body waves. We can also retrieve the body waves, but majority of the time it's easier to get the surface waves part of the Green's function. Mostly because the noise sources are acting on the Earth's surface, okay? And so, surface wave generation is really the requirement is just that the waves are trapped, in near the surface, and then it decays with depth. So this property of the surface wave make it such that it's easier to really retrieve the surface wave signal from the cross correlation. And so if these signals are actually surface wave signal, then we can use the consequences that we can use earthquake-based surface wave tomography methods or processing methods to retrieve and invert for the noise-based measurements, okay? Because now the point is we have now recorded a surface wave. Then this surface wave is the same as having an earthquake here and generating some source and some waves, and then the waves being recorded at this station. So if we have this recording, which is the same as, comparable to a surface wave signal that is recorded from an earthquake, then the processing method that we use to retrieve the velocity model from these surface waves coming from the earthquake, we can apply the same techniques to analyze the surface wave coming from the noise cross correlation. Okay, so that's the consequence of this. So then in the end, we have what it means is that we have bypassed the requirement for a source, and we're just using the noise-based signals, surface wave signals. So we just use the same techniques. Now, why this method is important? It's because traditional surface wave tomography has some limitations, okay? So one limitation is the inhomogeneous distribution of seismic sources and receivers. So if you look at the location of the location of say earthquakes, the first order information you get is that these earthquakes are happening, mostly in some concentrated areas, regions, and also the station distribution are not really uniform. Okay, I know if you can see this well, it's say on the continental part, I think this is the US. Okay, now it's covered with all stations, but before the station distribution wearing that uniform.
Hello?
And yeah, someone has a
It's
question.
morning. Can you hear me?
Hello. I didn't hear the question.
My network. I couldn't hear you. Like, I don't know whether it was my network.
Okay, sorry. Okay, I can repeat. This slide or before? Hello? Okay, let me repeat from this slide. Can you hear me now, by the way?
Yes, I can hear now.
Okay. So the point is why the ambient noise method is gaining more traction these days is it's because of some limitations from the surface wave tomography methods, okay, from earthquakes. Because one is the inhomogeneous distribution of the sources, the earthquakes and the receivers. Say if you are in a country where you need to retrieve a velocity model, but you have almost no earthquakes occur in your area, then you have to depend on some very teleseismic earthquakes. And also these earthquakes happens along some concentrated regions, and it's infrequent, I mean, the frequency of earthquakes like strong earthquake that you can really record at properly from teleseismic distances are not that many. And again, surface waves surface, so there is a direct surface mostly sample prefer. Yeah, and then so let's say we know that say the earthquakes are usually concentrated in this area, so and you have your seismic source, even if you have sources, okay, then in this case the travel path is almost always from this area to this to the stations you have. And so you cannot really constrain the velocity of the area behind these source, because once the wave propagate past these stations, there is no other stations to recall them. Okay, what you need is for the sources for another source to be in this area, so you can really constrain this. But sometimes this is not the case, so you are only giving just the sources at this in this area of your study region, and then there is nothing you can do. So this is a limitation, and inversion of requires some information about the source. Yeah, also we need some location about the source to do the inversion. So let's say because you remember U is a convolution of the source and the medium. So if we are interested in retrieving the medium properties, the elastic properties, then we need some information about the source, which is the location, travel time, and depth, and sometimes these informations are not known accurately. And in this case, it affects the travel time estimation. So then your estimate estimate of the elastic parameters won't be that accurate because of the errors coming from your the earthquake data. Okay, so this is also another limitation. And measurements of teleseismic waves provide average. Yeah, also, let's say you have an area here and your earthquake is located here. Then the travel path, it's from the source to the receiver. Okay, so all the greens, all the elastic properties is all the velocity, the arrival time, or the travel time is just due to the elastic properties of all the mediums between the station and the station and the source. But let's say you're interested in only finding the velocities of this area, but then the information contained in the wave you recorded is just an average of the medium properties between the source and the receiver. Okay, so then you're getting some information that you're not really from areas that you're not interested in. So it's difficult to really constrain the main the actual velocity of your area of interest because your data is average over some region. Okay. And also difficult in measurement of, okay, yeah. And also, let's say if your source is located here, difficult in measuring short period measurements from teleseismic surface waves. So if your source is located in this area, say some, I don't know, 100 or 1,000 of kilometers away, and because of attenuation, okay, the low period signals, okay, high frequency signals will be attenuated. So by the time you record your waveforms, there will be no information of the high frequency part of the wave, okay, because it's attenuated. So in this case, and remember that the high frequency parts are much more constrained the shallow part of the structure. Okay, so if you record only low frequency data or high long period data, then it means that you cannot have a good constraint of the shallow part of the crust, okay, of your area of interest. Then you're only left with constraining or imaging the deeper structures. Okay, so these are some limitations. And okay, I don't have it. But in the case of, say, these limitations can be removed if we consider just the ambient noise method, because now what you have is you have some stations in your study area, okay, and the point is each station can serve as a source if we cross correlate the noise signals. So the cross correlation between this station and that station will provide some information between these two stations. And because the stations are close by, you won't lose the short periods. Okay, so the high frequency part of the data will still be recorded. So you can constrain the shallow part, and you can and from this to that, from that to that, you can make the cross correlation, and from this to that. Okay, so this is just one part. And so the limitation of directions and earthquake sources are also removed, because now we can also do the cross correlation. Because we have already done this, we can take this station, do the cross correlation between this station and that station, this station and this station, and this station and that station. And then again, you do between this and that, this and that. Okay, this and that is already done, this and that is already done. Okay. And then lastly, there will be another one that you can do. I think this station and that station. Okay, so now we can really constrain the velocity in this area of our study region. Now, if we have more stations, say located in this area, okay, at this part of our study area, then in this case, it gives us a much more high resolution, because now we can also do the cross correlation between this and that, that and that, and these and that, okay, and these stations. So then in effect, I know this yellow thing is not showing well. In effect, we can really resolve the velocity structure in our area of interest, and all the information, it's just the average of the medium in our area of interest. So we don't have to care about the velocity in this area, because our wave is really not sampling these regions, which we are not interested in anyway. Okay. So then this is the power of the ambient noise. It helps us to really it helps us get some data information from just our area of interest, and then that's it. Okay, and these noise sources are always recorded, so they are always available. You don't have to wait for some number of earthquakes to get a good resolution or good constraint of your velocities. And you can do this every time and in any area, as long as you have some station distribution. Okay, so this is the power of it. So now we go through some the processing steps that you can do, just to give you an idea how to turn the noise source into signal. Okay, so with the ambient noise processing, it's mainly based on four principal phases, which are written here. So the first phase is a single station data preparation. So let's just take the example of just two stations. So we have two stations, and we record the noises or the waveforms here at both stations. And then the single station data preparation is just that we're just focusing at each station, we do some processing on this recorded waveform, okay, on this noise signal, and then we do also some recording, some processing on this recorded waveform individually. Okay, then the next phase is to now, once we finish with this pre-processing of these noise signals, is to now cross-correlate these two signals. So we cross-correlate and we get one resulting waveform, okay, where you see it was the positive and negative waveform. And then we do some stacking to improve the signal to noise ratio. We look at each one of them individually later. And then now the next one will be, okay, we've done our single station preparation. We've cross-correlated the data and we've stacked. We have to do some error analysis and quality control. Is this resulting waveform any good, or is just noise? Okay, so we have to check if we are able to really retrieve a signal or it's just noise. And then once we ascertain that there is really a signal that's propagating between these two stations, then we go ahead and use the earthquake available methods for earthquake surface wave analysis to analyze these waveforms, like measuring the dispersion curves and then going ahead and doing a tomography. Okay, so now we go into details so the single station preparation. So let's say we have the raw data. Okay, you record the raw data. So here in these two stations in the United States, we recorded the data, because the stations are recording continuously. Then what we do is to this raw data is to remove the instrumental response. We remove the mean. Okay, we remove the trend of the data. Then we do some filtering, and then we cut the data into day length. This is dependent on what you want to do. So what it means is that, say you have, from March 1st, okay, March 1st to say 30th of March or 31st March, your station is recording continuously, okay? And so then first you remove the instrument. So let's say you have this time series, then you just remove the instrumental response. So you deconvolve. You remember that the other day we said that the earthquake, the waveform is the source, convolve with the medium, and convolve with the instrumental response, okay, with the station response. So the first thing is to deconvolve this out of the waveform, and then now you remove the mean, and then you remove the trend. Okay, you remove the mean of the signal, and then once you remove the trend, if that, you know, when there's your time series is having a trend, then you remove the trend, you set it around 0, and then you do some bandpass filtering. And then now this is like a 1 month data. So I'll say, okay, I want to cut this data into 1 day time series. Okay, so I cut this signal into 1 day time series, so that, say if this is the whole, say this will be a 24-hour data. So this is 1 day. This 1 day thing, you can also, for some works, they even can cut it into 1 hour, okay, or say 12 hours. So you can just cut your waveforms. The point is to cut your waveforms into some time length. And then once you do that, you apply time normalization. There are different methods for the normalization, and then you do spectral whitening. The point for this normalization is that now in the first part, in the ballistic tomography part, where we're interested in the surface wave tomography from earthquakes or everything, or the P wave and everything, like we're interested in the earthquake. That time the earthquake is the data, okay? But with noise cross correlation, now the earthquake is a noise. So we have to find some method of removing the earthquake from the data. So this normalization technique will take away the earthquake signals from the data. So what is left is just the signal coming from just the noise sources distributed around the stations. And then we apply spectral whitening, which is to broaden the frequency, the amplitudes of the frequency ranges, okay? And then, okay, so this is a figure of, so let's say we record this time series. You see the earthquakes are hiding in here in the noise. If we do some filtering, we see that the earthquake pops up. So these are earthquake signals, so different, 2 earthquakes in the signal. And then once we do the normalization, we get these holes in the signal. That is, we remove the earthquakes. Now, if we bandpass filter, you see the amplitudes of the noises are uniform, relatively uniform. Now we got what it means is we got rid of the earthquakes. So because now the earthquakes are noises, so we find a technique to remove these noises. Okay, and then we have a uniform amplitude signal in time. And then the next phase was the cross correlation and stacking. So we compute cross correlation. So we take the signal coming from CCM, this station, and then from that station, and we perform the cross correlation. Now remember, this is a 1 day signal. Okay, this is the point. This is a 1 day signal. If you cut this is also 1 day signal. If you cut your continuous time series into 1 day. If you cut it into 1 hour, then it will be a 1 hour or 1 hour signal, or 12 hours, whatever you want. Yeah, because depending, sometimes if, let's say, you record for, say, 4 years continuous waveform, then cutting into 1 hour, 1 hour each will be like a huge amount of data. So then it's preferably to cut into 1 day. But if, say, your record length is, say, 1 year, or say some 6 months, then cutting into one hour, it's much more better, because I'll say what the reason, like just after this. So now when we cross correlate, then we get the 2 waveforms. So this is the 0 lag, so this will be the positive lag, so this will be the station. Sorry, this will be the signal traveling between the 2 stations, and then this is the negative time lag signal. Now you see, like we discussed before, the arrival times of these two signals are the same, but the amplitudes are different. And this is because of the inhomogeneous distribution of the noise sources, okay? And why we cut into this 1 day signal or 1 hour signal is because we have to stack the cross correlation. So we cross correlate first the two, so let's say in the example I said before, it's from 1st March to say 30th March, okay, our signal. So in this case, we cross correlate 1st March from station 1 and 1st March from station 2. And then we again do another cross correlation for 2nd March, okay, then 3rd March, up to 30th March, okay. We do this cross correlation. And so now we have 30 different cross correlations, okay. That is just the same signal that is traveling between these two stations. Then to improve these, this final signal that we're interested in, we stack all the time series, all these cross-correlated time series. So we add the 1st, 2nd, 3rd, up to, we stack all the 30 results together, and that gives us a final cross-correlation signal. And that one, if we do some filtering, we can see the cross correlation. So same thing, if we have 1 hour data, then we cross correlate the 1st hour, the 2nd hour, the 3rd hour, the 4th hour, and then we stack all the hourly data together, and then that will be our final results. Okay, this is how you go about it. And so, yeah, so if you, in the end, if you you do some filtering, you see that your signal is popping up. Now the Green's function here is different from here. Sometimes people will just take the part of the data that has the highest amplitude. That's because you have you will see when we talked about the signal, the quality control, you have a good signal to noise ratio in this part than in this part of the timeline. So what you can do is to take only one part, or in the usual case, you can also find the average between these two signals, because the travel time information are the same, okay, and it's the same medium. So you just cut this into 2, and then you flip this onto this part, and you average the 2 signals, and then this will be your final results that you analyze. Now, once you do that, you have a final result that will be something like this. And if you do some filtering within some frequency bands, some periods bands, you can see that you have a wave that is propagating, okay, propagating in time. So it's just a surface wave. Now, why? Because look at this. These are the long periods, and so they are arriving earlier in time than when you have all the short period data, the high frequency data. That's what these are, surface wave properties, because the long periods are sampling the deeper structure, so they are affected by the high velocity structure, so they travel faster, so they arrive faster in time than the high frequency content of these of the resulting cross correlation. So this is a surface wave, okay? And so now we have our surface wave, and the next part is that, okay, now we have our surface wave, we have to do some error analysis, and the commonly done analysis is to measure the signal to noise ratio. So we take some signal window, and then we take some noise windows that's after the signal, and then we find the amplitude ratio, of the signal window against the noise window, and then we find some SNR values. And in practice, the higher this value, the more pronounced your surface wave signal, okay? And then in usually in practice, you can even retrieve the surface wave from from using signals with SNR values of say 7, 10. Okay, so then if the number is big, then your signal is really prominent. But even if you get like 7, SNR value of 7, it's enough to really see a dispersion curve or a surface wave propagation. And so now we have a surface wave, and then the thing is, okay, it's a surface wave. Now it's the same as the surface wave you get from an earthquake. So you can use the technique for earthquake surface wave analysis to apply the same techniques to the surface wave coming from the noise cross correlation. So we can do a multiple filter analysis to measure the dispersion curve like we did yesterday. Okay, so now your signal won't be the earthquake signal, but it will be the results of your cross correlation. And then you can measure your dispersion curve, group, or phase velocity. And so we see that, yes, the measured cross correlation, the measured dispersion curves have the same characteristics as dispersion curves coming from earthquakes, where phase velocities are increasing and you have the group velocities that are low, have low velocities than the phase velocities. So this is it. So now you have the data. Once you have this data, then you can go ahead and do your 1D inversions and everything. But because now we have more data, and these data are coming from some 2D region, we can make the tomography, okay? So then we talk about the ambient noise tomography. So we have the advantage is the evenly distributed sources. We create a high resolution tomography images because now we can really constrain all the different cells, okay? Because all the different cells, at least there is some wave travel time information in each cell, so we can constrain the velocities properly. And we have, like I mentioned before, we have short periods that can help us constrain the shallow part of the crust. So some application examples. This is the work done in California. So we see that the ambient noise tomography method produce very high resolution models where you have your dense station coverage. So like I explained, these are in rectangles are the stations. And then you make the cross correlation. So all the lines, all the black lines in this figure are the two station cross correlation. So here, this station is cross correlated with almost all the stations. And then we can also make the cross correlation for each pair of station, we do that. And then these are the lines, okay? These are the travel time lines. So you can see that, let's say if this is our steady area, this whole rectangle is our steady area. And let's just imagine this is the acoustic tomography case where all the different grid lines are all these cells are we are interested in getting, say, constraining the velocities in all these cells. Then you can see that around this area, we have some data that will help us constrain the velocities in this cell, because the travel times, we can add the travel times together in this cell and find, try to constrain the model parameters, these velocities in these cells. But in this area, there is no travel time information, so we cannot really constrain the velocities, okay? So this is what tomography is about. And so if we plot, if you do tomography, there is some analysis. If we do this analysis, we can see that, okay, in this area, we cannot resolve anything. Okay, we cannot resolve anything. But at least in the areas where we have the rays crossing, especially this part where the rays crossings are dense, we can resolve structures on the order of, say, 40 kilometers or less, okay? So this is a high resolution area. And then you can see that as you go towards the northwest, the ray crossing becomes lighter, so then the resolution decreases to the northwest of the steady area. Whilst in this area, there is no ray crossing at all, so we can definitely get no information about the velocity. And so we use the travel time information between these two stations when you do the inverse problem, and then you can get the velocities. Okay, so this map, the velocities are color coded. So here we have a velocity. So this is the final result of a tomography problem. You produce a map. So this map will show you how the velocities are distributed in your study area. So here we can see that the velocities range from 1.4 kilometer per second to 4.0 kilometer per second. And this is at a period of 7.5, okay? So what it means is that within this period, so 7.5, remember that when with surface waves, if this is your Earth structure, Z, then the shorter periods are much more sensitive to the shallow part, okay, to the shallow part. So if we are looking at 7.5, probably we are looking at the velocity distribution at say 5 to 7 kilometers, okay, within the crust, okay. So the information we're getting is that within, say, at about 5 to 7 kilometers, there is a low velocity. Okay, so now the red color code indicates a low velocity because it's 1.4 to say 2.5. So there is a low velocity structure. Oh, no, that's not a good color. Which one would be good? Okay, I think white. There is a low velocity structure that is oriented northwest, southeast, okay, along along the faults. So these black lines are the faults in California. And also we can see another low velocity structure here. Okay, so this is how then you interpret your velocity models. And then there's another low velocity here, okay? But then there's a very strong low velocity anomaly you can see within this area, because here these are, say, 1.4 kilometer per second. These are low velocities. And then you can now, and okay, let me finish. And then the high velocities are popping up here. You see 3.5 to 4 to 4.0 kilometer per second. There is not much trend to it. Okay, they are just randomly distributed, so it's discontinuous. But then you can see it in here. So this is your velocity distribution. So the high velocities, and then there is also some low velocities, that occurs randomly within, spotted low velocities within the area. And then there is this gray area that is between 2.6 and 2.8. So these velocities occurs within this area. So these velocities information are coming from the inverse problem just by using this data, okay? And now once you have a velocity model like this, you try to associate it with some geological features. So usually low velocities are associated, especially at the crust, at crustal depths, to sedimentary basins, okay? So we can say that there is a sedimentary basin in this area, and then also in this area. And then the high velocities are popping up because of the igneous rocks, So these are, then you can really characterize your lithology and your structures just from the ambient noise data. So it provides the same information as you get from surface wave analysis using earthquakes, okay? So that's how it's done. And another thing is, now you can also I mean, okay, earthquakes, you can get lav. We know that earthquakes have lav and Rayleigh waves. You can get the same information with the noise cross correlation. So the technique is, if you remember that the Rayleigh waves occur on the Z and the radial component, whilst the lav wave occur on the transverse components. Okay. So if we do the cross correlation between the two Z components of the two stations, then what we retrieve here is the Rayleigh wave signal. And if we do the cross correlation between the two radial components, then again we'll get another Rayleigh wave. But if we do the cross correlation for the transverse component, then we'll get the lav wave. Okay. And you can see it's interesting because now you see that the lav wave travel time occurs earlier. You know, the lav wave travel faster than the Rayleigh waves, and this is the same information you get. And then you can see that the Rayleigh waves, the signal is almost appearing equally in time on the two components. Okay, so then this signal will give you your lav wave, and this two will give you your Rayleigh wave. So depending on which tomography you want, I mean, the data with a surface wave, you can choose to only investigate Rayleigh waves or lav waves. Okay, and the point is you can get this same information from just the noise cross correlation, so that you can use this to give you your Rayleigh wave tomography or your lav wave tomography. Okay, and so I think these two maps shows the lav wave tomography using ambient noise method for stations in the United States, and this is the Rayleigh wave, this is the lav wave, and you can see that the information, the first order information, the patterns of the velocity distribution is almost the same. Okay, there is a low velocity, a pronounced low velocity anomalies in these areas. Let me change to white again. In these areas, and again, it's here. You can see the same, almost the same information here. And then there is a pronounced low velocity here, but here the amplitude is not that strong. But then you can see the low velocity trends in the northwest, and then the high velocities occur in the eastern part of the United States. So then and first order information is that you can divide the United States geology into two, where the western side is mainly sedimentary rocks or sedimentary basins, because you have a low velocity structures, and then the eastern side is consists of some igneous rocks, so there is a high velocity structures. Okay, the same information from the lav wave, and these two maps are coming from just the cross correlation of the noise. Okay, so yeah, you can make your these are the same thing. So these are the noise. Oh wait, let me try and move this. Sorry. Okay, these are the noise. Oops. Okay, so this is the final cross correlation for the ZZ component, the radial component, and the transverse component. You can see that the lav wave is appearing earlier in time than the Rayleigh wave signal, same as you get on a seismogram from an earthquake. Okay, and also depending on your station, how wide your station distribution is. Okay, how wide your station distribution is, you can do continental scale or regional scale tomography. So, and this map shows the tomography map of the whole Europe. Okay, so here we are using station distribution from all these countries in Europe, and then you can make a continental scale map. So you can see there is this low velocity here around north and in the Adriatic, and some high velocities in this area and everything. So then you have a good idea of how the velocity is distributed. This is at 30 seconds, so these are it's at around mid-crust hour depth, say at 20 kilometers 20 kilometers within the lithosphere, or 20 to 30 kilometers within the lithosphere. This is how the velocity is distributed. And also you can make it on regional scales, which say a regional scale can be, say you want only the tomography map of Italy. In this case, it's say New Zealand. Okay, so these black triangles are the stations that you use for your cross correlation. And then you can get a highly resolved image of your velocity structure. Okay. Again, you can also image the crust and upper mantle. So how is to really get some information about the upper mantle, you just need your stations to be the interstation distance to be wider, okay? Because if they are wider, then your signal can travel a bit deeper before appearing. So then you can the signal is sensitive to the deeper structures. But in the case where your study area is very small, such that the station distribution, the interstation distance is not that great, then you cannot really go deeper within your lithosphere. So you are limited, at least in depth, in the depth range. But say if you do a continental scale tomography like this, using almost stations at each end of the continent, then you can sample up to 80 kilometers. So you can have an idea about the crust and the mantle structure, velocity structure from the noise signal. And again, you can also have an idea of the crustal thickness. So yesterday we said surface waves are usually not cannot really constrain the discontinuities, okay, within the lithosphere. But in practice, what we use is to use some velocity contours to describe the crust mantle boundary. So the MOHO, in terms of defining the MOHO with surface waves, we say, okay, if you have your 1D, say if you have a station and you have your 1D velocity model, okay, and then let's say another station and we have another 1D velocity model, okay. Then with surface wave, with models coming from surface wave, we can define some velocity, say at 4.2, okay. And we say, okay, the velocity at 4.2 indicates mantle velocities. So then in this model, we look for where 4.2 occurs. If 4.2 occurs, say in this at this depth, then we assign, say if this is 35 kilometers, we say, okay, the MOHO depth at this below this station is at 35 kilometers, okay. And say, so then in this study we are assigning it as 4.2, and if 4.2 occurs here, and say here is 55 kilometers below this station, 4.2 occurs in this area, then we say that the MOHO crust mantle boundary occurs at 55 kilometer depth below the station. So this is how you define some discontinuities, but this is the major discontinuities. You cannot we don't really do it for some very shallow, not pronounced discontinuity. We just usually do this for the MOHO. But the point is that we usually use the receiver functions because this velocity contour is very random, okay? It's some magic number. Well, I mean, it's accepted, but someone can also choose 4 point. The point is someone can also choose 4.0 and then define the MOHO as the depth where the velocity crosses 4.0, okay? But at least with receiver functions, we can really constrain this depth. But why we keep using this technique is that even if you do this analysis using just this velocity contour, and you define some crustal thickness based on just this velocity contour. If you compare the results to the discontinuities coming from receiver functions, they really approximate the results from the receiver function. So in some cases, in a case where you don't have any receiver functions, this is a good approximation. Using this velocity analysis is a good approximation to constrain the crustal thickness, okay? And so if we look at this work is showing, I think this is in South Africa, the crustal thickness from receiver functions, and using this analysis, this kind of analysis for the ambient noise to constrain the crustal thickness, okay? And if you compare these two figures, you can see that you're almost constraining the crustal thickness using the ambient noise or the surface wave technique. Okay, although here we see that the thickness is much more, let's say, towards 50 kilometers. But okay, the first order information is really good. And this is the results when you do the joint inversion, like we talked about yesterday, using just the ambient noise and teleseismic tomography. Okay, so what it means is you combine the ambient noise, the dispersion curve. I think there is a slide that explains this. And then you add also the surface waves coming from the earthquakes, and then you can also constrain you can use that to constrain the velocity and also the thickness. Okay, you see here now there is a much more thicker crust, but you don't see that only in the ambient noise method. So this is some analysis you can do using the ambient noise method. So also we can combine, like I just said, we can combine the ambient noise data with other seismological data. So we can do, what it means is we can do a joint inversion one, or we can just combine the data. Combining the data is the case where you have, because the ambient noise is giving you a dispersion curve, okay? And if you have an earthquake, you record an earthquake. The earthquake, the surface wave part of the signal is also giving you a dispersion curve. So in this case, it's almost the same data. So you don't do a joint inversion, but you combine the data. So let's say if the earthquake, so remember I said that the interstation distance put a constraint on the maximum period you can go. Okay, so let's say in your area, your maximum station distance is say 1,000 kilometers or 800 kilometers. Then it puts a constraint on the maximum period. Okay, so you can get your period from say 1 second to say, let's say 50 seconds. Okay, now this maximum period is coming from your interstation distance. But now your earthquake signal, if you record some earthquake dispersion curves, remember we said that because of the teleseismic distances, you lose the lower period. So your earthquake signal will be from say 25 seconds to say 140 seconds period, okay? So now, if you can combine the 1 second to 50 and then the 25 to 140, so that you have a dispersion curve that is from 1 to 140 seconds. Okay, so you can constrain from the shallow crust to the deeper mantle. Okay, and then in this case, in the area where there is a crossover, what you do is to just average the velocity from the ambient noise dispersion curve and the velocity from the surface waves, and then the earthquake surface waves, and then you just get one dispersion curve data, and then you use that to retrieve your structure. Okay, so then it gives you a much better constraint from the surface, from the crust, shallow part to the deeper mantle. You can even constrain your model up to 350 kilometers if you want, okay, by just combining the data. So kind of each data contributes to some parts where you have a good resolution of the earth structure. So this is what you can do to retrieve a high resolved velocity model. And examples of structures. Yeah, okay, so teleseismic dispersion curves. Then once you have your 2D models, you can have some profiles, and these are just some presentation of the data. So you have what it means is to get these vertical structures, you should have the 2D tomography. So let's say if this is 2D tomography for say 5 seconds, then you have another one for 10 seconds, then you have another one for say 15, and so on and so forth. Then you can have a vertical cross section, through the whole tomography 2D slices, and you get a 2D horizontal slice, and you get a 2D vertical slice. And then you can see how the velocity. So in the case where you have your figures are presented in this case, in the horizontal slices, you are looking at the distribution at some depth. Okay, so let's say if this is at say 50 kilometers, this is the velocity distribution in your area at 50 kilometers. Now, if we pick a profile, say from this point to this point, okay, and we have a vertical profile, then we see how the velocity varies with depth along this profile. So this is what it means. So then we can see, okay, the low velocities are occurring at the upper the shallow part, which is good, and then the velocity increases with depth, from theory. Then these are just the first order information, but what are the interesting things we're looking for? What these changes in low velocities. Okay, so then you are looking for the abnormalities in the velocity models, and you try to associate this to some tectonic process. So you have we call these. So you see there is a low velocities within some area along your profile, and you try to explain why or associate these low velocities to some tectonics. So you can see this high velocity that is popping up is explained, probably it's a slab that is being subducted, so it causes this high velocity, and then this low velocity is maybe some magmatic chamber, or some molten rocks, partial melts, because of, say, you have a high temperature. This is a high temperature region in the mantle. So then you can associate these velocity distribution to some temperature or chemical or compositional distribution of the materials in the mantle and in the crust. So these are informations you get from your tomography models, okay? And then now we can also, remember yesterday we talked about joint inversion of receiver functions and surface wave dispersion curves. You can do the same thing here. So we know a receiver function, we can compute a receiver function from a recorded earthquake waveform. And then we can, these are some processes, so you can generate a receiver function. And this will be your surface wave signal. And then you can we talked about this yesterday, you can do the inversion for only receiver functions. We do the inversion for only the surface waves, and we can also do the joint inversion, okay? So now in this case, the dispersion curve is coming from the ambient noise tomography data, okay? And then you can do that. So then in summary, what is that with this analysis, surface wave analysis? It's a well-established method for now estimating the earth structure, okay? And then the ambient noise green function. It has now become a well-known and well-understood process to study the Earth velocity model. And why this is important is because the ambient noise method allows us to image aseismic areas, regions, because in the cases like I explained where there is no earthquake sources or infrequent earthquakes, then you can really use just the noise sources and the station distribution to really get a constraint on your velocity, the velocity model of your region of interest. And because of also the different dominant periods of the ambient noise, which is mostly at the low period signals, and the long periods coming from the surface waves, okay, because you can have periods from say 25 to say 150 seconds. You can get, combining these two, like the example, you can get a high resolved image of the lithosphere. And also we can use it in conjunction with receiver functions to get a robust model of the Earth structure. So this is it. This is the end, and this is just to give you another idea about ways you can retrieve your velocity model, not just from earthquake signals, but also using this new and very interesting technique. Okay, that's it. Any questions?
I have one curiosity.
Yeah.
What kind of instrument do we need to record for seismic noise?
No, any broadband station.
Okay.
Yeah, any broadband station you can, or even the long, just a long period station, because the service waves long period. So just even if you have a long period station, yes, you can. You just need a continuous station.
Okay.
You just need a continuous station, and then you are good to go. Yeah, that's just it.
Okay, thank you.
Any other question from the class? Okay, so then I think I stayed in time this section, so it's almost 4 minutes left. So we'll end the class, and then you try to. I think you have an exams today and also some other sections tomorrow. So, but you please try to write the code like yesterday I said, and then we can discuss when you're ready, and then you send me, and then we can go through it, because it's important to know how to move from just the model to the inverse problems and everything. Okay, I think it will help you to understand better mostly what we talked about with the inverse problem. Because in the end, most of the codes are already written, and you're given the code and you have to change it to suit your problem. So once you know where to change and what to look for, then that's good. So that's the idea. Okay, so if there is no further questions, then we can end here and talk to you guys some other time.
Okay, thank you.
Thank you.
Okay.
Thank you.
Okay, bye.
Bye.
It's morning.
Hey, Jacobo.
How are you?
Fine. Are you ready for the exam?
Oh, I would say 80%. Seriously, I have to check.
Well, don't worry.
Yeah.
If you're positive, she will ask about the things that you know best. So
yeah, sure. I have to read a certain paper and then about the methods. She sent us the summary, so I'm sure maybe she'll be asking about something about the method, the windows we chose and those stuff. Yeah. So I want to read over mine. This one I submitted to her. Just prepare for, like, sit for it. I think it will start at 2 or something. Yeah. And Tarek too is not well. I said Tarek, he's not well.
Yeah. You, I heard when you said it at the beginning of the lesson. Too much stress, too much exams. Too many exams.
It's true. It's not easy. It's not easy. So see you, and I will contact you when we are done.
Okay. Good luck for the exam.
Okay, thank you. Bye-bye.
Bye.